Here's a really simple example, but still worth mentioning. Let's say that we have the function f of n equals 100. It's a constant. So for any input length or for any number n that you put into f of n, you always get 100 out. Claim is that f of n is big O of 1. Usually you see like n or n squared or 2 to the n inside here, but f of n here I'm going to say is big O of 1. So why is that? Well, remember we need to prove that there exists c and k such that for all n greater than k, f of n is less than or equal to c times 1, because we put a 1 in there. So I'm going to choose my constant c to be 100. And k, again, we'll pick to be 1. So then we need to prove that for all n greater than 1, f of n, which is 100, is less than or equal to a constant c, which we chose to be 100, times 1. And you can see that n doesn't appear on either the left or the right-hand side, but that's fine. For all n greater than 1, it is definitely true that 100 is less than or equal to 100. In fact, 100 equals 100. So this implies that f of n is big O of 1. So just another way of saying that f of n is a constant. You know, if I'd put 1,000 here, or 10,000, or 100,000, or 1,000,000, any constant that doesn't depend on n, so f of n is a constant, that function, in that case, if f of n is a constant, then f of n is big O of 1. So remember, we said that f of n is big O of g of n whenever for sufficiently large n, f of n is always less than or equal to some constant times g of n. Now there's also something called big omega notation. And we say that f of n is big omega of g of n. In words, this roughly means that for sufficiently large n, f of n is greater than or equal to some constant times g of n. So very crudely, big O sort of you can replace with a less than or equal to sign. Big omega you can replace with a greater than or equal to sign. Okay, so more mathematically, more precisely, we say that f is big omega of g of n if there exist constants c and k such that for all n greater than k, the absolute value of f of n is greater than or equal to some constant times the absolute value of g of n. Okay. So for sufficiently large n, so f is big omega of g of n if for sufficiently large n, f of n is greater than or equal to some constant times g of n. So let's do an example. Let's let f of n be n squared over 100 and g of n be n squared. Then it is the case that f of n is big omega of g of n. So just rewriting this, I'm saying that n squared over 100 is big omega of n squared. Why is that? Well, we need to produce constants c and k such that for sufficiently large n, for all n greater than k, n squared over 100 is greater than or equal to n squared. So we need constants c and k such that for all n greater than k, n squared over 100 is greater than or equal to c times n squared. So I'm going to choose c to be 1 over 100 and k to be 1. Then we need to show that for all n, so we need to show that for all n greater than 1, n squared over 100 is greater than or equal to 1 over 100 times n squared. But this is self-evident. I mean, n squared over 100 is equal to 1 over 100 times n squared, so certainly for all n greater than 1, n squared over 100 is greater than or equal to 1 over 100 times n squared. So this implies that n squared over 100 is big omega of n squared. Okay, so n squared over 1,000 is also a big omega of n squared. N squared over 1,000,000 is also a big omega of n squared. Remember, the big O and the big omega usually hide constants. Let's do another example. Let's prove that f of n equals n times log n is big omega of n. Okay, so we need to show that there exists a constant c such that for all n k, such that for all n greater than k, f of n is greater than or equal to that constant times n. So I'm going to pick the constant c to be 1, and this time I'm going to pick k to be 2. And we need to show that n times log n, this is log base 2 of n. When I don't write the base, it means log base 2 of n, is greater than or equal to constant 1 times n, and then we need to show this for all n greater than 2, because we picked k to be 2 here. But notice, if k is greater than 2, if n is greater than 2, it implies that log base 2 of n is greater than or equal to 1. Right? If n equals 2, then log base 2 of 2 is 1. And log is an increasing function. So if we choose n to be larger than 2, it means log base 2 of n is greater than or equal to 1. So on the left-hand side, we have n times log base 2 of n, which is something bigger than 1. So log base 2 of n. And we need to prove this is greater than or equal to n times 1. And again, for n greater than 2, this term is greater than or equal to 1, and n is greater than or equal to n. So the left-hand side, so this implies that for all n greater than or equal to 2, n times log base 2 of n is greater than or equal to n times 1. And this implies that n times log n is big omega of n. So this is a case where, you know, if we had chosen k to be 1, if you plug in n equals 1 here, the log base 2 of 1 is 0. So this left-hand side would be 0, and 0 is not greater than or equal to 1. So that would be a problem. But by choosing k to be 2 for sufficiently large n, this left-hand side does get much larger than n. In fact, n log n, you know, it's not difficult to prove that n log n is big omega of 5n. N log n is big omega of 100n. You know, n log n is big omega of 1000n. And that's because no matter what constant you put here, 5, 100, 1000, 10,000, as you may, for n sufficiently large, this log n is an increasing function. So it's always going to be, it's going to get bigger than whatever constant you write. You know, if you tell me 10,000, then eventually log n will be, when n is larger than 2 to the 10,000, log n will be larger than 10,000. So all of these functions are big omega of any constant times n. And finally, very briefly, if f of n is big O of g of n, and f of n is omega of g of n, then we say that f of n is theta of g of n. And this also is often said that f of n has the same order as g of n, or is of the same order as g of n. We'll talk more about this in class.